Welcome back, ladies and gentlemen. Today we're going to be continuing on our graphing review. We're going to be talking about velocity time graphs, and so if you guys pull out your notes, we'll be taking a look through them. So obviously, I'm going to be referencing right here. So first things first, of course, a velocity time graph is going to show the velocity of an object. And the thing about velocity time graphs is that they're actually, in some ways, the most useful graph because they're the most flexible. Now, the downside to them being the most flexible is that it also means that there's the most ways that you can mess up when you're doing them. But what can you do? So when you're looking at this, you'll see in the notes that it tells you that there are two ways that you can use a velocity time graph. You can use the slope and you can use the area. Now, slope, you already have done a bunch with. Area is going to be probably a bit new. Well, I mean, sort of new. You did do it in grade 10, but, now you'll be like, oh, yeah, I remember it. So first things first, we have to remember, and this is key, everything is relating to the y. So a negative y means that I'm going to be moving backwards. Y equals 0 means not moving. And y equals some sort of positive number, I'll just put it the same way as we did the others there, positive y means that you are moving forward. Now, remember, this all comes down to the fact that when we're talking about positive and negative in physics, we're not talking about like positive is gain, negative is lose. We're talking about direction. So positive means forward, negative means backwards, okay? Or, north positive, south negative, or right positive, left negative, whatever, some pairing of directions in a dimension. Okay, so that's the key thing that we have to understand there then. We also then can continue, and we're going to talk about slope. Slope we've done tons of when we did the position time graphs. So the slope, which remember has the symbol handwritten M, don't know why, they just chose that. So the slope has three basic shapes, it always does. We've always got the flat line, the sloped line, and the curved line. Now the key thing here is that we don't have to worry about number 3. This doesn't show up in a velocity time graph. And the simple reason for that is because, remember, this means changing acceleration. We don't do that. Well, that sort of gives away the game. What do the other ones mean? This means acceleration is 0, and this means that the acceleration is some number. We don't know what. So that's the big difference with the shapes compared to a position time graph. In a position time graph, a flat line meant that I wasn't moving. In a velocity time graph, a flat line means that I am continuing to move at the same velocity. There's no acceleration involved. Now, keeping that straight in your head can take a little bit, but it's important, okay? So that's the acceleration part. That's the slope part, I should say. That part, pretty familiar, right? It's still going to be the same basic equation. If we do our equation right, the equation for a slope is going to be, oh yeah, we're not doing this. The equation for the slope is going to be delta y over delta x. And for our velocity time graph, y is clearly going to be delta v, and x is still going to be t, so it becomes delta t. That is the literal definition of acceleration from our notes. Okay. So that part is pretty familiar, right? There's no real surprises there. At least I hope not. If there are, ask me questions. What about the other part I said? Area. So area is one of the reasons why the velocity graph is so flexible. But it requires a little bit of reminder, a little bit of explanation of things. So we're going to take a look here at option B. We're going to look at area. And to do this, we're going to need a graph. I have a ruler, may as well use my trusty ruler. So we're going to put a graph over here, nothing too fancy. You've got a quick sketch of a graph in your notes. There we go. And we're going to go like so. There we go. And it's a velocity time graph, so I'm going to do it in blue. I generally try, to do the different graphs in specific colors as sort of a visual clue to you which type of graph we're talking about. Because unfortunately, as we've discussed, they all kind of look the same because they're just lines. And, by themselves, lines don't tell you too much. All right, so wait a second. The example that we're going to deal with is a little different than the one I originally did. There we go. So we're going to deal with an example that looks kind of like this. It's going to go over like so. Later on, there's another section that's over like so, but under the axis. And then we're going to connect the two with a nice diagonal line. All right, so there's our velocity time graph that we're going to analyze in just a second. If you already remember how to do this stuff, feel free to pause the video, try analyzing it yourself. The numbers, of course, are in the notes. I haven't written them down yet, but, give it a shot. All right, so the thing about area that we have to remember is that this is going to be an area calculation. Now, here's the thing, right? Velocity has a calculation. The definition of velocity looks like this. Now, we can maneuver this equation, right? We can change this to say delta D, and I'm going to move the t over, is going to be equal to v times delta t. Now, the reason why this is going to be useful for us is because that means that right now in our particular graph, v is y and t is x. And this is the magic. This is the area of a square, base times height, for example. Or maybe you know it as length times width. So what this basically means is that the area under the curve represents the displacement. Now, the phrase area under the curve tends to get a little bit of confusion here because I don't know how many times I've seen students, if I do a real quick one here, I don't know how many times I've seen students do something like this. Right, here's a very quick sketch of a graph, and I'll tell the students, all right, area under the curve, and they'll go, okay, got it. I remember that from math class. So there's this area here. Okay, that's a triangle, and then there's another area here. That's another triangle, and then they'll do a square right there, and that part will be fine. And then they'll get here, and they'll go, okay, so I'll just go like this, and just go all the way to the bottom of the page because they're thinking area under the curve means, below the line. And that's like reasonable because that's exactly what happens up here. But when we're underneath the axis, it's no longer that the area under the curve is down. The area under the curve then becomes between the graph and the x-axis. And that's kind of the key here. The phrase area under the curve is kind of a shorthand. It's like a saying that mathematicians developed to mean the area between the curve and the x-axis. If you're above, which most graphs are, that means the area below. But when you go down here, it means above. So can that be a little bit confusing? Yes, but just be careful. We're going to also see, as we do this one over here, that the shapes are not always going to be quite as simple as just little triangles and squares, right? We got to make sure that we do it properly. Okay, so that's our reminder about how area works, but now let's get some numbers in here. Let's get some work, okay? So the numbers that we've got in the example, it's on the second page. Let's put out some numbers on our graph. So I have chosen, this is going to be 2. This here will be 4. This point will be 6. This point will be 8. And way over here I did 13 because apparently I decided to make things difficult for myself. So with that in mind, we're now going to break things down. What we end up getting here is that we put all of this into various sections. We always want to divide up the various sections of the graph in order to make it as clear as possible what's going on. So over here, as you saw when I did the little sketch, we're going to divide this up into segments, like so. And the thing about these segments is that we generally try to do them wherever we find some kind of a change in the shape or when we cross the axis. So those are sort of the two main things that we're looking for, okay? We're looking for change of shape. We'll put it over here. We could also add another one. Change of shape, change of sign, or cross the axis. So those are our three criteria for when we cut up the graph. So in this case here, I cut the graph at those locations because here I go from a flat line to a slope line, so that's a change of shape. I also go here across the axis. So this is one area, this is another area. That's a change across the axis there. So we cross the axis. And then here I go from a slope to a flat, so that's another change of shape. It could also happen, for example, that we end up going, say, up and then down, right? The shapes are the same, but one of them's positive, one of them's negative, so we would have two different sections there. Okay, so this we're going to call section 1, and it's a square. This is going to be 2, and it's a triangle. This is 3, and it's another triangle. And then we've got 4, which is another square. Now you'll notice that for the end here, even though it doesn't technically end in any way, I just took it all the way to the axis, right? So this is where I sort of cut off things. If there's something else after this, doesn't matter. I don't care. So I put all that together, and now I need to collect my information and start solving. So I've got my 1, 2, 3, 4. I put all that together, and what do I get? Well, over here I've got the area of a square. Number 4 is also the area of a square. These ones are areas of triangles. You'll notice I'm just using the symbol for square and triangle in order to write that down. I could have written the word square or triangle or really just done nothing of the sort, but this way at least I'd know what I'm talking about right away, and it's a lot less work on my part. The formula for each of these areas is going to be assembled. You're going to have base times height over 2, base times height over 2, and base times height. So now we just need to put in our numbers. Now, the first one is pretty easy for a number, right? Because its height is 2, so it's going to be 2 here, times the base, which goes up to 4. All right, so we got 4 times 2, and then we're going to get 8 meters. Okay, that one's pretty easy. And we'll just write it down right here, just so we can keep track of it. So this one here is 8 meters. Now, the next one isn't as easy. I mean, it's not hard, but it does require us to think a little bit, because the height of the triangle is still 2, right? Like from here to the top is still 2, so that part stays the same. But the base of the triangle is a little different. It's not 4 and it's not 6. It's 2 because it's the separation from 4 to 6. So this could be written just as a 2, or I could do 6 minus 4 in brackets if I wanted to be all algebraic. And then it's all divided by 2 because it's a triangle, so it's half of a square. Okay, so we put this together. Bit of algebra reminder, guys. These 2's cancel, so it's really just 6 minus 4, so that means it's going to be 2 meters. All right, so we write down right here, this one is going to be 2 meters. Next triangle. Next triangle is basically the same thing, right? It's 6 to 8, so it's still going to be a total of 8 minus 6 for the base. The height is going to be a little different, though, right? Because the height now is negative. So the height is going to be negative 2 all over 2. Now, once again, it's not going to be very hard to do this math, because I at least selected somewhat of a simple answers or numbers to try and solve, except for the last one. I don't know what I was thinking. 13, that's never easy. But there we go, negative 2. Finally, we got the last one. The last one is going to be from 8 to 13. So we're going to go 13 minus 8, and it is still minus 2 in terms of its height. And over 2? No, because it's a square. See, I just got lazy and bored, right? I kept doing minus divide by 2, divide by 2. So now we're going to take what is that? Going to be 10, I think, in total? Yeah, negative 10. Now, to be clear, do you need to do this every time? No, not even slightly. Like, this is stuff that you guys first learned back in grade 7? I think it was 7. So if you don't want to have to write it out, go right ahead. That's fine. I'm doing it step by step because these are notes, so I want to make sure you guys have as much as possible. Okay? So there we go. We've got all our information. Now we need to start figuring out what all of this means. This is the part where, like the math here is pretty straightforward, but there's something else we've got to take into consideration. Because all of these calculations found delta D. Remember, the formula that we used was this one. V equals delta D divided by delta T. So if I put that together and I rearranged it like I did, I get delta D equals V times delta T. Now, there's nothing wrong with that. That just tells us the displacement. So, for example, in the first segment here, from the start till 4 seconds later, I will cover 8 meters. That's what that tells us right there, 8 meters. The second segment, I'll cover 2 meters. Both of these are positive, so they're both forward. This one, though, is negative, which means I will go 2 meters backwards. But where am I at that point? I mean, I'm not at 2 meters negative because I went 8 and then 2 this way, and then I came back 2. So in order to figure out what's going on, we have to remember what the definition of displacement is. Displacement is position final minus position initial. Let's clear some space. So if we put all of that together, what are we going to get? Well, all of these numbers that I've calculated down the side here, all of these are delta D. All of these. But I just asked you, what is my final position at the end of segment 3? The way you would do this is figure out, of course, what's my initial position. The way you set this up is that we're going to move with some algebra di over to this side, right? So we add di to both sides. These two cancel. I'll rewrite it. So we're going to get the final position, which is what I asked you for, is equal to the displacement plus whatever the initial position was. Well, what was our initial position at the end of section 2? It was 8 and 2 more. So initially we were at 10 meters. Then we had a change of minus 2. So that puts us at 8 meters. Positive. So even though this number is -2, that doesn't mean that we go to the position -2, right? Like if I were to draw a position time graph of this, very quick sketch here, I don't go like this. I don't go, all right, so I start off and I go up to 8, and then I go down to 2, and then I go -2. That's not what happened. I didn't go like this, boop, boop. Instead, what happens is I started off going to 8, I went up, then I went 2 more, I go up, and then I come 2 down, I go there. Right? That makes more sense. I go forward, I go backward. And then, of course, the last piece, -10. Oh, here's where the 13 comes in. This is why I did it. Because the last one for -10 means I'm at +8. I go backwards 10. So where do I end up? Down here at -2. There you go. That's the basic idea. So remember, when you're working with velocity time graphs, okay, area is to find the displacement or the position, and slope is to find the acceleration. When you're cutting up the graph, you're going to want to do it using these basic rules. But to be honest, you guys have had a lot of practice cutting up graphs in your other courses, so you'll probably be fine one way or another. all you guys need to do now is, well, practice, like a whole lot of practice. The booklet is full of practice at this point. I think it goes up to, I want to say page 30 something, might be even longer. Unfortunately, I had to give away my last booklet because a student didn't have one, so I can't check it easily myself. But you guys can keep going all the way through everything that is velocity time graph practice, and there's quite a few of them. I think the last one that you can do might involve a chap called Evil Timmy, who you will see a lot of in the coming weeks and months. That's about it, though. There is the reminder sort of review of velocity time graphs. You guys now have some information that you can sort of be armed with, and you guys can give it a try. Okay? So I will see you guys next time.